Right, so still on the topic of constant coefficient second order linear ODEs that are homogeneous. Let's just review what we did last time. So last time we talked about how to use the characteristic equation to solve one of these, and it was about as simple as solving a quadratic equation. So not really that big of a deal. Let's suppose we have the following initial value problem. Y prime prime plus 5y prime plus 6 equals 0, 6y equals 0. And we're given the initial conditions y of 0 equals 1, 1. And y prime of 0 equals -1. Now, I believe I went over this particular ODE last time, but I don't think I talked about it in the context of an initial value problem. You see, when you have a second order ODE, as you can see from the examples that we did last time, you have two constants of integration involved, C1 and C2. So that means that when you do an initial value problem, you're going to need two initial conditions. Something about y and something about y prime. Okay? But anyway, let's just review how we did this. So first thing that we had to do was draw the write the characteristic equation, which in this case is just going to look like r squared plus 5r plus 6 equals 0. Right? So that can factor. That can factor into r plus 2, r plus 3 equals 0. And then that gives us two roots, r1, which is -2, and r2, which is -3. Those two roots correspond to two linearly independent solutions to our ODE, namely y1, which is e to the -2x, and y2, which is e to the -3x. And so then we have the general solution as all the linear combinations of these two. So that would look like C1 e to the -2x plus C2 e to the -3x. And that was the general solution, right? Now let's talk about how to use the initial conditions to find the values of C1 and C2, to find a particular solution that solves our initial value problem. Well, let's see. First of all, this is a condition on the derivative of y. So we're going to need the derivative of our general solution. So y prime, that's going to be -2 C1 e to the -2x minus 3 C2 e to the -3x. And so then from there we can apply the initial conditions. We know that 1 has to be y of 0. Y of 0, according to this, is just going to be C1 e to the 0 plus C2 e to the 0. And then y prime of 0 needs to be -1. So -1 is y prime of 0. And so that gives us -2 C1 e to the 0 minus 3 C2 e to the 0. And then this is a system of two linear equations that we can solve for C1 and C2, just like in high school. Okay, so let's go ahead and do that. Let's see, I suppose the way I most prefer to solve this system is to multiply the first equation by 2. So that will get 2 equals 2c1 plus 2c2, And meanwhile, the second equation is still -1 equals -2c1 minus 3c2. Then you can add these together. The c1s will cancel, and we'll get 1 equals -c2. All right, in that case, c2 has to be -1. And then if c2 is -1, then that means that c1 has to be 1. Or I mean, not 1, 2. 2. All right. So then the particular solution that solves our initial value problem, we just put these constants c1 and c2 into the general solution. We get 2e to the -2x minus e to the -3x. And that is the particular solution that solves our initial value problem. Okay, so as I said last time, this process is made easier by the fact that the characteristic equation has distinct real roots. So today, what if the roots are not distinct or not real? That's what we'll talk about. So, if you have repeated real roots, it's not really that big of a deal. There is a pretty easy way to handle it. Basically, you're going to get an equation that looks like r minus something squared equals 0. That literally means r minus k times r minus k equals 0, right? And so then, normally what you'd do is you'd say, all right, well, that gives us two different solutions. One of them is k, and the other one, I guess, is also k. And then you're like, all right, well, that gives us two different solutions to the ODE. So we have y1, which is e to the kx. And then y2 is, I guess, also e to the kx. But then you have a problem. Then you have a problem because then when you want to apply Stolch, the solution theorem for linear homogeneous ODEs, these two are not linearly independent. In fact, they're not even different. So definitely not linearly independent. Okay? So you can't construct the general solution from these two. So what you have to do is get rid of this and create a new solution that's linearly independent to y1. How do you do that? You multiply it by x. That's it. Okay, that's how you handle the case of repeated linear roots. Now these two are, or repeated real roots. Now these two are linearly independent. You can check that using the Wronskian. And so therefore the general solution is going to be all the linear combinations of these two. Of course, we're going to do some examples. So, let's say we want to find the general solution of y prime prime minus 6y prime plus 9y equals 0. Okay, so characteristic equation looks like r squared minus 6r plus 9 equals 0, right? And then that does factor. That factors into r minus 3 times r minus 3 equals 0, or in other words, r minus 3 squared equals 0. So we have exactly one roots to this quadratic. It's 3. All right, well that gives us a solution. That gives us y1 equals e to the 3x. And now you'd like to say that there's another solution. There has to be another solution because you have to have as many basis solutions as the order of the ODE. Since this is a second order ODE, we're going to need 2 solutions to construct the general solution. You'd like to say it's e to the 3x, but you know that's not going to be linearly independent. So what you do is you just make it x e to the 3x. And then that does it. The general solution is now all the linear combinations of e to the 3x and x e to the 3x. And that's that. Okay? Now, I just want to point out, because people write it this way, this is equal to c1 plus c2x e to the 3x. Both of those are the same thing, right? We're just factoring out the e to the 3x from both terms. In any case, this is our answer for this example. Okay? All right, let's take a look at another example. Let's suppose we're going to solve the initial value problem. Y prime prime minus 8y prime plus 16y equals 0, with the initial conditions y of 0 equals 2 and y prime of 0 equals 0. Again, because we have a second order ODE, we're going to need 2 initial conditions, one for y and one for the derivative of y. Okay? So, characteristic equation just looks like r squared minus 8r plus 16 equals 0. That factors into r minus 4 times r minus 4, or in other words, r minus 4 squared. So that gives us exactly 1 real root, which is 4. That then gives us a solution. y1 is going to be e to the 4x. And then once again, we have no other root, so you can't construct the other solution based on the other root because, you know, it doesn't exist. But what we can do is just multiply this thing by x in order to get another solution. So y2 equals x e to the 4x. And then with these two, Stolch implies that because we have a second order ODE and 2 linearly independent solutions, the general solution is just all the linear combinations of those. So y equals c1 e to the 4x plus c2 x e to the 4x is our general solution. And again, this can be written as c1 plus c2x e to the 4x. Now, we're not done. We're not done because we've just found the general solution, whereas the initial value problem is asking for a particular solution that satisfies these 2 conditions here. So let's continue. Let's see, y of 0 is supposed to be 2, so let's see here, 2 equals y of 0. That's going to be c1 plus c2 times 0 times e to the 0, which, you know, is just c1. And then y prime of 0, it has to be 0. So we're going to need a derivative of this. Y prime is going to be, let's see here, 4c1 e to the 4x plus 4. Actually, we need to do the product rule. So it's probably easier to just take the derivative of this thing then. So first times derivative of the second plus the second times the derivative of the first. Looks like that. And so this becomes, let's see here, we have 4c1 plus c2 and then 4c2x multiplied by e to the 4x. Okay, so that's important to us because y prime of 0 is supposed to be 0. So 0 has to be y prime of 0. And that has to be, let's see here, 4c1 plus c2 plus 4c2 times 0 times e to the 0, which just comes out to be 4c1 plus c2. Okay. So again, this is a system of equations that we can solve for c1 and c2, although in this case the first equation is just telling us straight up that c1 is going to be 2. So c1 is 2. As for c2, well, we know that 0 is going to be 4 times c1 plus c2. So that means that c2 is going to have to be negative 8. And so what that means is that the particular solution that solves our initial value problem is going to be 2 minus 8x times e to the 4x. And that is that. Okay. So that's how you take care of repeated real roots of your characteristic equation. There's one more possibility, right? As you learned in high school, a quadratic equation could have distinct real roots, repeated real roots, or non-real roots, complex roots, right? So what do you do when you have complex roots to your characteristic equation? Well, there's a way to handle that. And it's using a theorem known as Euler's formula. Euler's formula says that for every real or complex number x, e to the ix is cosine x plus I times the sine of x. All right? So let's look at an example and see how this works in action. Let's suppose we're looking at y prime prime plus 9y equals 0. That's a perfectly ordinary differential equation, right? That's a perfectly normal problem that we could easily get, right? So the characteristic equation in this case is going to be r squared plus 9 equals 0. All right. That has no real roots, because in order for that to be true, r squared would have to be negative 9. So then r has to be the square root of negative 9, plus or minus the square root of negative 9. Or in other words, plus or minus 3i. Okay? Plus or minus 3i, where I hope we remember from high school that I just refers to the square root of negative 1. So, we have this, and then normally what we do is we take e to the rx, right? We do that here as well. Okay. We have the complex solution e to the 3ix. You might be thinking, what about negative 3ix? We'll get to that. So this thing right here, what exactly is it? It's not easy to understand what exactly this function does, right? So in order to understand what it does, we need to rewrite it. This is e to the I times 3x, right? So then according to Euler's formula, that is going to be cosine of 3x plus I times the sine of 3x. Right? Okay, very well then. But this is still a complex function, a non-real valued function. You take any value for x, what you'll get back is some non-real number. Unless, of course, the sign is 0, but that's not the point. So the question is, how do you find real valued functions that would solve this ODE? There's an answer. We have a theorem that says if a complex valued function is a solution of an ODE, then I think we actually have to say it's a linear ODE. Yeah, it has to be a linear homogeneous ODE with real constant coefficients then its real and imaginary parts are solutions of the ODE. Now, first of all, let's just recall what we mean by real and imaginary part. So every complex number can be written as a plus bi, right? Or a plus ib. Real part refers to this real number right here. Imaginary part refers to this other real number right here, b. Arrow, arrow. And I want to emphasize the real part and imaginary part are both real numbers, okay? This real part is the real number a, whereas the imaginary part is the real number b, okay? A lot of students think that when you say the imaginary part, you're including this I. You don't include the I, okay? In any case, the theorem says that if we have a complex valued function like this, then in that case, the real part, so if we have a complex valued function that's a solution of our ODE, which we do, that's the case here, then the real part, cosine 3x, and the imaginary part, sine 3x, those are separately solutions. And they're real valued, right? So let's call this y1 and this y2. Now at this point, we have y1 equals cosine of 3x, y2 equals sine of 3x. Two different solutions. You can check using the Wronskian that they are indeed linearly independent. Therefore, the general solution of our ODE is going to be all the linear combinations of these. C1 cosine of 3x plus C2 sine of 3x. And that's the general solution. Okay? Now, if you're waiting to see what happens to the negative 3i, the answer is we don't need it, right? We don't need it because we already found the general solution. So we're good to go? The directions just said find the general solution, and we did. The truth is, if you took the negative 3i and put it here, it would give you the same information. So it just doesn't matter. You can just take one. And I would recommend you always take the plus rather than the minus. Okay? So this is how we deal with non-real roots. We need to use Euler's formula to rewrite the complex solution in a form where it has its real and imaginary parts apparent. And then just pick out those real and imaginary parts, and then those form the general solution. Okay? Of course, we're going to do some more examples. So suppose you want to find the general solution of the following ODE, y prime prime plus y prime plus y equals 0. Again, that's not any more unreasonable than any other ODE we've worked with. But nonetheless, it will end up having complex roots, the characteristic equation. because the characteristic equation is r squared plus r plus 1 equals 0. All right, so now that you have that, you look at this and you say, all right, the discriminant, b squared minus 4ac, if we remember from high school, b squared minus 4ac, in this case, is going to be 1 squared minus 4 times 1 times 1, which is definitely a negative number. Since the discriminant is negative, that means that we have no real roots. So, the roots are non-real. We can figure them out using the quadratic formula. Negative b plus or minus the square root of b squared minus 4ac divided by 2a. All right. So let's see here. This turns into negative 1 plus or minus the square root of 1 squared minus 4 times 1 times 1 is simply negative 3. And then divide that by 2. So then, that is negative 1/2 plus or minus I times root 3 over 2. And those are the roots of our characteristic equation. All right. So now this is a little bit different from the previous example, because in the previous example, there was no real part. The real part was 0, right? Whereas in this case, we actually have a non-zero real part and also a non-zero imaginary part. That's fine. We do the same thing as we normally do. We put this into e to the rx, which in this case is going to be e to the negative 1/2 plus I root 3 over 2 x. Again, we need only take the plus. Don't bother with the minus, it's going to give you the same information. Distribute this. This becomes e to the negative 1/2 x plus I root 3 over 2 x. Now, Euler's formula says e to the I times whatever equals something. But that's not exactly what we have in this case, right? In this case, we don't have just I times something. We have I times something plus another thing. So, we can handle that because we have addition in an exponent here, right? If we have addition in the exponent, then we can write that as a product of two exponentials, e to the negative 1/2 x times e to the I root 3 over 2 x. All right. Now, Euler's formula applies to this factor. Not this one, though. Not this one, because it has no I in its exponent. But that's fine. We can just leave it, because it's a real valued function, right? So that's not the problem. The problem is this thing. So we apply Euler's formula again. This turns into e to the negative 1/2 x times, okay, e to the I theta is cosine theta plus I sine theta. So this is going to be cosine of root 3 over 2x plus I times the sine of root 3 over 2x. Distribute that. Distribute that, and what you get is e to the negative 1/2 x times cosine of root 3 over 2 times x plus I times e to the negative 1/2 x sine of root 3 over 2 times x. Right, and now we have a real part and an imaginary part. So, our real part is this function right here, which we'll call y1, and our imaginary part is this function which we'll call y2. And now again, we can check using the Wronskian that those two are linearly independent. The point is that they are two linearly independent solutions to this second order ODE. So therefore the general solution is all the linear combinations of those. C1 e to the negative 1/2 x cosine of root 3 over 2x plus C2 e to the negative 1/2 x sine of root 3 over 2 x. And that is our general solution. And by the way, people will sometimes write this differently too. Sometimes they'll factor out the e to the negative 1/2 x and write this as just C1 cosine of root 3 over 2x plus C2 sine of root 3 over 2x. And of course, that's the same thing, right? Okay. So, that's how you deal with constant coefficient, second order linear homogeneous ODEs. If you have distinct real roots, you can just construct the two solutions, take all the linear combinations. If you have repeated linear roots, you can construct one solution, then multiply by x to get the other solution. And if you have complex roots, you can use Euler's formula to convert the complex solution into a form where you can read off the real and imaginary part, and then those construct the general solution. In any case, that's all for today. See you in the next one.